Section 9.5, dilations. Think of this as what happens to your eyes whenever you go to the eye doctor and they put the little drops in your eye and your pupils dilate, they get bigger. That's what we're going to do with the shapes. We're going to make them bigger or we're going to make them smaller. So this one is not an isometry because the shape is not the same as what it started as. All right? So this is official definition, transformation whose pre-image and image are similar. They are not the same size. This is a new word for you. Similar just means that they look the same, but they're not the same size. Okay? It is not an isometry. So when I ask about the types of isometries, this one is not one of them. Every dilation has a center and a scale factor. The center is what the shape gets bigger or smaller from. So it gets farther away from the origin or it gets closer to a point, something like that. And then the scale factor is what is how big it gets. So it gets 2 times bigger, it gets a third as big, it gets 10 times bigger, whatever. Okay? These are the two things that you have to have in order to do a dilation. All right, 2 different types of dilations. There's an enlargement and there's a reduction. These should be self-explanatory just by listening to them. An enlargement means it's getting bigger. The shape is getting bigger. So the scale factor will be greater than 1. It could be 2 times bigger. It could be 1.5 times bigger. It could be 3.5 times bigger. Something like that. It just has to be bigger than 1. A reduction is a scale factor between 0 and 1. So small fractions. Half as big, an eighth as big, 3/4 as big. Those are all reductions because it's less than 1. And we're going to do both. All right, so when you look at this, there's 2 triangles here. The red is on top of the blue. And it says the blue triangle is a dilation image of the red. So that means we started with the red, we ended with the blue. So describe the dilation. Obviously, it's an enlargement because the blue triangle is bigger than the red. So it goes from the red, it goes to the blue, it gets bigger, so it's an enlargement. We have to figure out how much bigger. Okay? The only side we have to compare is the longest side. So it starts out as 4, but then it goes to this entire side, which is 12. So it starts out as 4, goes to 12. That's 3 times bigger. So the scale factor is 3 because it gets 3 times bigger. And then we need a center of dilation. A good clue is a point that doesn't change. And so the point that doesn't change is this x down here. So your center is at x because everything gets bigger away from the x. All right, same deal. The blue is a dilation image of the red. Describe the dilation. So if we start with the red, we end with the blue. This is a reduction. So we have to figure out how much smaller it gets. So let's just take one set of points. We'll look at this point and this point. So we started out here. This is 6, -4 is where we started. It shrinks in to 3, -2. So look how far it's shrinking. These numbers are half of what they used to be. So your scale factor is 1/2 because they're half as big. And everything is getting closer to the origin. Because if you look at these other points, they're half what they used to be towards the origin. So the center is 0, 0, the origin. Okay, so whenever we describe a dilation, you're going to tell me the scale factor and the center of dilation. All right, we can also do scale as part of dilations because a scale model is just a reduction of an original model. So this says packaging lists a model car's length as 7.6 centimeters. It also gives the scale as 1 to 63. So if you guys have little brothers or maybe you had toy cars at home or whatever, a scale factor means that it takes one of the big ones is actually 63 of the little ones. So it takes me 63 Hot Wheel cars to make one big car. Okay, so a 1 to 63 scale we can use for stuff. All right, they give us the model car length of 7.6 centimeters. So that means it takes 63 of the 7.6 centimeters to make the big car. Okay, so I'm going to take 7.6 times 63 and figure out the actual length of of the car that the model is supposed to be like. So that would be 478.8 centimeters. Now you're saying, that's cool, that's great. And I say, you can't measure your car in centimeters, that's just not practical. But this happens to be, if you moved your decimal place for centimeters, this is 4.8 meters. That makes more sense in my brain because I'm talking about a car. I'm talking about something big. All right, here we have the height of a tractor trailer truck. So the big truck is 4.2 meters. The scale factor for a model of the truck is 1/54th. So it takes 54 little ones to make one big one. I want to find the height of the model to the nearest centimeter. So last time we multiplied to get what we needed to get. Okay, this time you divide because you're going backwards. So you start with the height of the truck and you divide it by how many little trucks it takes to make it. And when you do this, you get 0.08 meters. And that's well and good, but how many of you actually know how many 0.08 meters is? So I'm going to change this. I'm going to move my decimal place. This is 8 centimeters, which makes sense for the height of a model truck. Alright, so let's put some stuff on a graph and let's play around with this a little bit. We've got point P at 2, 0. And we've got point Z at -1 and then a half. -1 and then a half is right there. And then we've got G at 1, -2. Okay, so there's our triangle. Alright, wants to know the coordinates of the image of P for a dilation with center 0, 0 and a scale factor of 3. So that means everything gets bigger by a scale factor of 3 from the origin. So everything gets 3 times bigger. So if we look at the triangle, we'll just do the whole triangle. P is at 2, 0. It goes all the way out to 6, 0. So it goes all the way out here. P prime 6, 0. Because it gets 3 times as big. Z is at -1 and a half. So it goes to -3, 1 and a half. Because it gets 3 times bigger. -3, 1 and a half. And then G is at 1, -2. So it goes to 3, -6. It's 3 times as big. Okay, so that triangle got 3 times bigger. That actually means its area gets 9 times bigger. If you want to know that, I can show you how to do that. Alright, one more. Same triangle, so we'll go P, and then Z, and then G. Alright, there's my triangle to begin with. This time, I want to know the coordinates for a dilation that's from the origin with a scale factor of a half. So it gets smaller. It's half as big. So if P starts at 2, 0, it goes to 1, 0. So I'll put 1, 0. And then Z is at -1 and a half. It goes to -1/2, 1/4. So Z prime -1/2, 1/4, because 1/4 is half of a half. And then G is at 1, -2, so it goes to 1/2, -1. G prime 1/2 negative 1. So this triangle right here is half the size of the old one. Okay, dilations are a little tricky, so you need to be careful about what your scale factor is and what your center is.